Hello everyone. Today, JB and I will be presenting the angle addition and subtraction formulas and cofunction identities. So here presented are the sine and cosine angle addition formulas. You should all go ahead and write these down and start memorizing them because they're going to show up a lot in your coursework and they're very important to know by heart. So go ahead and write them down now so that you won't have to later and begin memorizing them. This is a helpful way to memorize them. So for sine, you can think of the s in sine as same sign, because if you look at the two formulas for sine, the sign on both sides of the equation stays the same. And the c in cosine can be thought of as change sign, because the sign is opposite on both on both sides of the equation. And there's also a rhythmic pattern to the way the functions are ordered. For sine, it's sine, cosine, cosine, sine. And for cosine, it's cosine, cosine, sine, sine. So just use those two methods to remember these functions, or these formulas rather, and you should be good to go. So here are some problems. The first type of problem you'll encounter is finding the exact value of an angle that is not commonly known on the unit circle, like 30, 45, or 60. In this example, it's 75. So how do we do this? We split up the angle into a sum or difference of two angles that we know. So for example, 75 equals 45 plus 30. And so we use this to apply the formula we just learned. Now we already know values like cosine 45 and sine 30, so we just substitute them all in and then we simplify. And that is our answer for the exact value of cosine of 75. Now the next problem is similar. It's finding the exact value of sine 105. This time we're going to use the difference 150 minus 45. And so we apply the difference formula for sine, and we substitute and simplify. This next problem is the reverse of the last two, where we have an expanded form and we have to convert it back to the original function. In this case, it's the addition formula for sine. So we put this back together and we get sine 60 as the result, which we all know from the unit circle. Now here is a proof. So yeah, here shown is a proof, and the way we solve these is we select one side of the equation and manipulate it until we arrive at the other side. So in this case, we're going to select the right hand side because we see in the numerator there's an opportunity for expansion with the formulas we just learned. So we expand with the angle addition formula for cosine, and then we split up this fraction here and simplify down, and we arrive at the left hand side. So the proof is complete. And this next proof is a little bit more challenging. We first select the left hand side because we see that the left hand side has opportunities for expansion in two places. So we then expand it out with the formulas, and we FOIL this, and the second and third term actually cancel out. So we are at this, so right now. And for the next part, we actually have to recall that the Pythagorean identities, so cosine squared y equals 1 minus sine squared y, and sine squared x equals 1 minus cosine squared x. And we use these identities in this expression. We expand everything out. And actually we see that the second and fourth terms cancel out, so we arrive at our solution. And the proof is complete. So now we've talked a lot about sine and cosine, but you may be wondering, where's tangent? We can actually figure this out on our own using these formulas, and I'll show you how exactly we do that. So we set it up like this, and we use the addition and subtraction formulas to expand the right hand side out. And we divide the top and bottom by cosine A, cosine B in order to aid in simplification. And there you go. That is the formula that will show up if you Google it. So I think we've done it correctly. And the formula for tan of A minus B can be derived similarly. So now this is the last example, and it's a very important one as well, because this type of problem shows up very commonly in this unit of coursework that you are currently doing. So it's very important that you all know how to solve these. So the problem simply states, evaluate the expression under the given conditions. The expression here is sine of theta plus phi, and it gives us some information. So the first thing you always want to do is look at the expression. Is there expansion to be done? And in this case, yes, we need to apply our angle addition formula. So we do just that. And the problem gives us sine of theta and cosine of phi. So all we have to do is plug those two in. Plug those two in. And we're left with two unknown values, cosine theta and sine phi. So in order to solve for these, we have to create two right triangles, one in quadrant 1 for theta and one in quadrant 2 for phi. And now all we have to do is simply use the Pythagorean theorem to solve for these missing sides. And we do just that. And so we plug these values in now for sine theta plus phi, and we can completely solve for it now. So we just simplify, and we get 2 square root 5 over 65 as our answer. Now it's worth noting that 12 over 13 and square root 5 over 5 may not always be positive. If theta was in quadrant 2 instead of quadrant 1, for example, it would be negative 12 over 13 because the cosine of theta in quadrant 2 is negative. So it's just something to keep in mind. You don't want to screw up the signs when doing these problems because it'll really mess up your answer, and you really don't want to mess these ones up. So pay careful attention to the quadrant that you're working in. All right, that is all. Now we will turn it over to JB for the cofunction identities. Thank you for watching.